Hello, I want to first thank the organizer for giving me the chance to give this talk. I will speak about algebraic Frobenius manifold and its relation with classical W-algebras and semi-universal deformation of simple singularities. And the problem I work with is a classification problem about Frobenius manifolds. And these Frobenius manifolds appears in many fields of mathematics. Maybe you know that. So the algebraic Frobenius manifold, or the problem I am working with, is related to somehow the singularity theory, the invariance theory of finite groups, and the classical W-algebras. So I give you something about the definition of Frobenius manifold, classical W-algebras, and a conjecture due to Dubrovin about the classification of these algebraic Frobenius manifolds. So this is the definition. Actually, the Frobenius manifold comes from the definition of WDVV equations. I call it geometric WDVV equations. And what we are looking for a function in n variables with a special index. Here my special index will be n. Such that the third derivative of these functions, where here you have Tn, it is a non-degenerate constant matrix. And this function f satisfies a system of partial differential equations. It comes from topological conformal field theory. It is known as WDVV equations. And these equations depend on the third derivative of my function f, where here my metric eta is the inverse of this constant matrix. And this system of partial differential equations is supposed to be satisfied for all index I, j, q, r. If you wonder what is the difference between the left-hand side and the right-hand side, is just you have these two index ti and tr. You have to reverse them here. Okay, and we are looking for this function so that this function is quasi-homogeneous. You give some degrees to the variables ti, and when it acts on f, it gives you some degree. And this degree, if you put it in this case, 3 minus d, so you have to normalize dn is equal to 1, and here d will be called the charge, and these degrees will be called after the degrees of Frobenius manifold. So before we go to, I have to give you some examples. So here there are examples in dimension 3. These examples you can actually construct by just looking to the WDVV equations, and you see the constraints. So these are in dimension 3. Here I lower the index. So you can see that these are polynomial solutions. All of them are polynomials. And the quasi-homogeneity condition, which comes from the Euler. We call it Euler vector field. And it gives you some charge. And these examples were introduced in 92 by Dubrovin. And in that conference, actually, Arnold noticed that the numbers here for the Euler vector fields in the 3 examples are related to Coxeter groups in dimension 3 or of rank 3, which is our as to the classification, it is A3, B3, and H3. And this will be the beginning of the classification problem for WDVV equations, or the partial differential equations. So, so the Frobenius manifold, geometrically, actually as defined by Dubrovin, you have to use the constant matrix eta ij to define a metric on the tangent space of your domain. And you define a product, as this product is defined by the third derivative of your potential f of t. You just raise the index. This gives you a kind of a product in the tangent space, and the product with the metric define for you a structure of Frobenius algebra. This Frobenius algebra in the tangent space will be a smooth structure, and this structure will be Frobenius algebra, and this Frobenius algebra have all the nice properties you can have. This Frobenius algebra will be commutative, and the particle index Dn will define for me a vector field. This vector field will be the identity element. And your metric will be invariant with respect to this product. And the WDV equation, the separated equation, the partial differential equations, it will be the reason for the associativity of this Frobenius algebra. Okay, so this definition of Frobenius manifold in these coordinates, here we use these coordinates. These coordinates will be called always the flat coordinates because the metric here is constant. And in these coordinates, we can define that the manifold M will be algebraic if my function f is algebraic function. That means it depends on a solution of some polynomial. And we call it semi-symbol if the tangent space of this algebra is semi-symbol for generic variable or generic point T. Okay, so this Frobenius manifold, of course, it can be constructed by looking to the metric and define the product. This was used also for singularity theory. They define the product and the metric, and then you see if it satisfies all these three hypotheses. Or it can be defined by using another object in Frobenius manifolds. And this object we will use actually in construction. This object is the flat pencil of matrix. So what we have two matrices on the cotangent space. We call them, and in the cotangent space, we call them flat if their inverse actually define a flat metric on the tangent space. And we can define the contravariant Levy-Civita connections of this matrix. We call them flat pencil of metric if any linear combination of these two matrices is also flat. Not only that, actually the Levy-Civita connection of this metric, it have also to be a linear combination of the Levy-Civita connections of these two matrices. This is the definition of flat pencil of metric. So any Frobenius manifold actually possesses a flat pencil of matrix. By setting the first metric to be the flat metric, we define it here. Sorry for that. It is a flat metric, and the other one is defined by the second derivative of my potential t. This will call it always the intersection form. Okay. This flat matrix actually satisfies for me some conditions. It's called the homogeneity condition of degree d. Here d is just the charge for my Frobenius manifold. Okay, so because the construction here actually will depend on flat pencil of matrix, I just write the definition of quasi-homogeneity and how we find flat Frobenius structure from flat pencil of matrix. So two flat pencil of matrix, that means they are flat and any linear combination would be flat. We call them homogeneous of degree d if we have just one function tau. The gradient of this function defines for me two vector fields. The first vector field will be the Euler vector field, will give me the quasi-homogeneity of Frobenius manifold. And the other one will give me the gradient with respect to other metric. It will give me the identity of Frobenius manifold. These two vector fields have to satisfy for me these conditions about the Lie derivatives. So the Lie derivative with respect to the first vector field or the Euler vector field of E is supposed to be minus E. And the Lie derivative of the second metric, it gives you d minus 1 of the second, so it is conformal. And here the degree appears, d. And the Lie derivative with respect to the identity vector field, it gives you the first metric, and for the first metric, it gives you 0. So quasi-homogeneity is actually for Frobenius manifold is a necessary condition. It's not a sufficient condition. For sufficient conditions, you need also a notion of regularity. So you have to define a metric by the Euler vector field, and this metric have to be non-degenerate. Okay. So from quasi-homogeneous regular flat pencil of matrix, we always get a Frobenius manifold. So here is just a simple example how we construct Frobenius manifold from flat pencil of matrix. And here is for Coxeter group of type A2. We know that this group actually is a symmetric group of the hexagon, and you have two reflections. This reflection defines for you a metric on the space of the Euclidean space, and you can lift this metric to the cotangent. Then you use the invariance theory. From the invariance theory, you know that the polynomial ring, the invariant polynomial ring, is generated by two homogeneous polynomials. This homogeneous polynomials is degree 2 and 3 in this case of A2, and the cotangent bundle will be just defined by the covectors of these two invariant polynomials. So the orbital spaces of this Coxeter group actually have two invariant matrices. The first one, it comes from the Euclidean space, and the second one is just the derivative of the first one. This for you will define for you a flat pencil of metric. And this flat pencil of metric will be regular and quasi-homogeneous and give you a polynomial structure of dimension 2. Okay. So we will use flat pencil of matrix to construct a polynomial Frobenius manifold. And from Arnold's remark about the relation between polynomial Frobenius manifold and the exponents of Coxeter group, we Dubrovin construct on the orbital space of Coxeter group a polynomial Frobenius manifold. So if you have a reducible finite reflection group and this is the exponents actually are related to the invariant theory of this Coxeter group. So by Chevalier's theorem, the invariant polynomials of the action of a reflection group are generated by R homogeneous polynomials of degree which are related to the exponents of the Lie algebra. So you take the orbital spaces, and these homogeneous or invariant polynomials will be the coordinates on the orbital spaces. So you construct algebraic Frobenius structure by using flat pencil of matrix. The first one constructed from the flat invariant metric, and the second one will be just, as this example, it will be just the derivative with respect to a high invariant metric. Okay, so this example was constructed in 1993. 10 years later, approximately, Hertling proves that these are all the set of polynomial Frobenius manifold. So we have a classification of polynomial Frobenius manifold, and all of them are related to reflection groups. They are polynomials, and we can actually read the degrees and the chart of this polynomial Frobenius manifold. The conjecture I'm working in is a generalization of this one. Instead of looking for polynomials, we are looking to algebraic. And the algebraic actually have another conjecture, and this conjecture says that the algebraic Frobenius manifolds correspond to quasi-Coxeter conjugacy classes in irreducible reflection groups. By quasi-Coxeter conjugacy class, I mean that a conjugacy class where you do it as a product of simple reflections in the minimal way. This reflection will generate for you all the group. So it is the biggest conjugacy classes in reflection groups. These conjugacy classes are already classified by Carter, and the conjecture says that this actually will give you all the algebraic Frobenius manifolds. And the classification of these quasi-Coxeter groups, quasi-Coxeter conjugacy classes in Coxeter groups, have this set. So in the reflection group of type AN, BN, CN, you just have just one quasi-Coxeter conjugacy class. This conjugacy class will be Coxeter conjugacy class. That means you have just the polynomial Frobenius manifold. And type Dn is an interesting type because when Dn actually goes to bigger, the conjugacy classes will get also bigger, and then you have infinite set of algebraic Frobenius manifolds. There is many things actually support this conjecture. First, the conjecture arises from deep theory in a Frobenius manifold, the asymmetric deformation of Frobenius manifold. It shows that if you have algebraic Frobenius manifold, then it will lead to some kind of braid group action of simple reflections. And this braid group actions of simple reflections is supposed to be finite, and it will be finite only if you have a quasi-Coxeter conjugacy class. So we know that if you have algebraic Frobenius manifold, we always get a quasi-Coxeter conjugacy class. So the problem we are doing now is just the existence of this algebraic Frobenius manifold, if they are exist or not. Also, the conjecture gets stronger because the asymmetric deformation of Frobenius manifold, when it is polynomial, it gives you the Coxeter conjugacy class in simple reflections, in reflection groups. So here is the polynomial Frobenius manifold actually was constructed by using the invariant theory or Chevalier's theorem. If you want to generalize this to algebraic structure, we don't have a corresponding theorem to use. So our solution to this problem is to go to integrable systems, mainly to go to local Poisson brackets. In local Poisson brackets, if you are truncated in very well way, you put some degrees on the, you make the derivative actually increase the degree of any variable by 1, and the Dirac delta functions is just of degree -1. You can truncate the Poisson of the local Poisson brackets by this way, so you have the leading term of degree -1, and then the degree 0, and then a bigger degree. And these have a finite interpretation, finite geometry interpretation. The first always is give you a Poisson brackets on your manifold M. And if this one is equal to 0, the leading term, the second term always, if it is exists, we say that this Poisson bracket or the local Poisson bracket admit a disproportionless limit. Then we have a theorem which says that if it admits disproportionless limit, that means the leading term here is equal to 0, and the determinant here is not equal to 0. This metric here is a contravariant and flat metric on the two cotangent space. And actually, the other term here is supposed to be just the Levi-Civita connection of this metric. So we look for a local Poisson bracket of this one, which admits a disproportionless limit, and the leading term is not degenerate, to construct algebraic Frobenius manifold. So the way to find a Frobenius manifold or a local Poisson bracket, which actually related to Coxeter classes in Coxeter group or reflections group, we go from reflection group, we go to while groups actually. So we restrict ourselves in quasi Coxeter classes in while groups. So if we use these restrictions, then we can use a correspondence between quasi-Coxeter conjugacy classes, and we have some relation with Nilpotent orbits in simple Lie algebra. And from Nilpotent orbit to simple Lie algebra, we can use the theory of simple Lie algebras, and we construct for any Nilpotent orbit, we can construct a local Poisson bracket. And this local Poisson bracket is known in the literature as classical W-algebra. Okay, so we can get a classical W-algebra related to quasi-Coxeter conjugate classes in while groups, and then from here we see that we take the disproportionless limit, to find a Poisson bracket of hydrodynamic type. Okay, this one, by using this theorem here of Dubrovin and Nevikov, we can get a flat pencil of matrix. So it is a long way. It is something like 4 steps program. And from the flat pencil of matrix, you get algebraic Frobenius manifold. So the first example of algebraic Frobenius manifold or polynomial Frobenius manifold was constructed by using these 6 steps, was given by Krishiver. And the second example was given by Pavlik in 2003. And we see that this actually is related to quasi-Coxeter conjugacy class in reflection group of type D4. And this conjugacy class, or this potential of Frobenius manifold, actually in 4 dimensions, and depends on this variable z, where z is a solution of this quadratic equation. Okay. And this is some history about classical W-algebras. Actually, classical W-algebras now can be constructed for any nilpotent orbit. And the construction here is well known. It is Dirichlet-Sokolov reduction. And Dirichlet-Sokolov reductions was studied in 2 ways. One way is to study the hierarchy of Dirichlet-Sokolov, and the other one is to study if it is a classical W-algebras or not. In 2002, actually, Weher and his collaborators, they generalized Dirichlet-Sokolov, the standard one, and they give a reduction for any nilpotent element, and they show also it is equivalent to Dirac reduction, and they construct the Virasoro densities. I will show it later, and the primary field of this classical W-algebras. So actually, we proved that actually this classical W-algebras can be constructed in 3 different ways. You have the Dirichlet-Sokolov reduction. You have by Hamiltonian reductions. The equivalence was initiated by Berdoni and Cassati. And you have also Dirac reduction. This gives me give us a powerful tools to construct these local Poisson brackets, the classical W-algebras, and to understand them. So, and each one actually gives you a different method to construct these local Poisson brackets. Okay, so we begin these steps, and we construct some algebraic Frobenius manifold. This one also in Coxeter group or reflection wild group of type F4 is if dimension 3, and here it depends on z, and z here is a solution of a cubic equation. It's not a quadratic equation. Okay, and we also succeeded to do this one uniformly for all polynomial Frobenius manifold. So what we have the relation between quasi-Coxeter conjugacy classes in wild group and nilpotent orbits. If you take here Coxeter conjugacy class, it will give you here some kind of a nilpotent element is called regular nilpotent element. And the construction here was done by Constant. And if you use this one and you go through all these steps, here you will find polynomial Frobenius manifold. But already we know all the classification of polynomial Frobenius manifold. We was looking for a uniform constructions, not for the polynomial but for the algebraic ones. The problem always is if you do these steps, to go from here to here, you have to be sure that actually you have a dispersionless limit. And always we need to do some kind of another Dirac reduction here. So you have two reductions, Dirac reductions in the first space to get local Poisson bracket, another Dirac reductions to get a Poisson bracket of hydrodynamic types. And to go here to here and use Novikov Dubrovin theorem about flat pencil of matrix, actually you need to show that the metric GI is non-degenerate. So we have non-degeneracy condition. So until now we didn't succeed to find a uniform way to do this algebraic Frobenius manifold. But the examples that we did here are related to, we give an infinite set of examples, and these are related to the Lie algebra of type DR. So I will show you how this was related. So the simplest way for me to introduce for you is this local Poisson bracket. It is a finely Poisson brackets on the looped space of the Lie algebra. So you define it by introducing some set of basis for the Lie algebra, and all the structure is constructed by finding the dual basis. So you define the Lie-Poisson bracket by using this dual basis. The leading term here will be just coming from the invariant bilinear form or the Killing form in the Lie algebra, and this one will be the structural constants. And so for any Nilpotent elements in the Lie algebra, you construct SL2 triples. That means you have E, H, and F, which satisfy for you the standard SL2 triples relations. And you construct this Slodov slice. This Slodov slice is an affine space which is constructed by the stabilizers of the Nilpotent element F. And it have a very deep theoretical origins, because if you take the action of the adjoint group on the Lie algebra, so we know that the Lie-Poisson bracket have symplectic correlations, and this symplectic correlations is just the orbits. So here you have the orbit of the Nilpotent element E. It have a symplectic structure, and this Slodov slice will be transversal to this symplectic structure. So here we have Q, and here we have the orbit. And so if you do the Lie-Poisson structure on these orbits, you find the classical W-algebras. By classical W-algebras, I mean that the variable which is corresponding to the Nilpotent element F, it will be a Virasoro density. And the other fields here, it will be a primary field. That means it have some kind of charge. And this charge actually comes from the theory of the Nilpotent elements. Okay, so look into this local Poisson brackets in a different way by this truncation. What we find that the first one here in this picture is the Lie-Poisson brackets, and the other one here is the reduction of the Lie-Poisson brackets on the Slodov slice. The leading term here, you can see that these are a Dirac formula for the reduction of Poisson brackets, the finite dimension Poisson brackets. This Poisson brackets is well known in people working in Poisson geometry. It's called transversal Poisson structure to the joint orbit of E, because you can show that the Poisson bracket actually is a product of this transversal Poisson structure and the symplectic structure on the orbit space. So because the formula here actually depends on the inverse of the metric, okay, it was a huge research to show that actually this structure is polynomial. Actually, they show that more than that, they show that it's a polynomial Poisson structure, and it is quasi-homogeneous if you give the coordinates some kind of degrees. Okay. Also, we can show that the same way that the leading term here, which after will give us Frobenius structure, also is quasi-homogeneous of some degree. And this degree depends on the interior Ij. Okay, so this is just the definition of of classical W-algebras, how it looks like, and what is the leading term. The leading term is transversal Poisson structure, and we have some kind of quasi-homogeneity condition, and all the interests actually are polynomial. When we go to restrict ourselves to subregular nilpotent element in Lie algebra of type DR, which is a special orthogonal algebra of type 2R. Okay, here we have, we can go deeper to understand the local Poisson bracket. And here we just choose R, so that the rank of the Lie algebra actually is even, for a reason I will tell you later. And what we will have, this the subregular nilpotent element in DR is related to deformation of simple singularities. So if you take the action of the adjoint group on G, we know that by Chevalier's theorem is generated by the same rank of homogeneous polynomials. And then if you take the map from the Lie algebra to CR by this homogeneous polynomial, this map is called the adjoint quotient map. The zero set of this adjoint quotient map is known as Nilpotent cone, and it has a isolated singularity. This proves that the reduction of this map actually to Slodow's slice, we define it later, is semiuniversal deformation of symbol singularity of the same type, DR. I don't know the proof of Brinscon. He did this in the level of Lie groups, but in the level of Lie algebra, Slodow was studying how to reprove this result. What he shows that actually the restriction of these invariant polynomials in Slodow's slice is quasi-homogeneous, of the same degree as the degrees of Coxeter elements. So any element here depends on the coordinates on the Slodow's slice, but the plus nonlinear term. If you take these coordinates, I will call it Slodow coordinates, the adjoint quotient will be just a projection. So you have a projection from T1 to TR plus 2 to T1 to TR minus 1. And here T0 is just the reduction of the highest invariant polynomial. If you take the zero set of this map, it gives you a polynomial of degree, in the three variables. TR plus 1, TR plus 1R, and here R plus 2. This polynomial is the polynomial which gives you singularity of type DR. Here C1 and C2 and C3 is some constants. These are very powerful results because it gives us the dependence of this variable T0 on the other variables. So using these coordinates, we find that the leading term of the transversal Poisson structure actually can be, we can know the interest. It is, the leading term will be almost zero except this 3 by 3 matrix, where this 3 matrix actually is an standard Poisson brackets of degree 3, which is defined by this variable T0. This variable T0 is just a reduction of the high invariance on of higher invariant on Slodow's slice using these coordinates. So if you use the Dirac reduction or the steps we show it here on this local Poisson bracket by this subvariety, you are sure that the leading term Fij will vanish, and you will have a Poisson bracket which admits a disproportionalness limit. This Poisson brackets will be also classical W algebra, but it will not be polynomial, it will be algebraic, because when you do the reduction on n, you have this algebraic relation between the variables. Okay, so what we get? We get a Poisson structure of hydrodynamic type on this subvariety Ln. And this is a classical W-algebras. And the leading term will give me a hydrodynamic type. That means I have a metric here, and I have to show that this metric actually is non-degenerate, so that it will give me a flat pencil of metrics. It turns out that the non-degeneracy condition here will be related to, I have to show that the determinant of G of Rs is doesn't equal to 0. And we show that it doesn't equal to 0. The relation comes actually from here, from the relation between the quasi-coexistent conjugacy class and the Nilpotent element. Okay? So we show that it is non-degenerate, so we have a flat pencil of metrics. This flat pencil of metrics will be generated by this set here and the derivative of this set. I'm sorry, because of the time, I cannot tell. There is many technical details which I cannot actually explain now. So because of the time, so what we get algebraic Frobenius manifold, and this algebraic Frobenius manifold actually satisfies for me a very weak relation. We cannot actually construct the isomorphic deformation or the mononomial group of this algebraic Frobenius manifold. But we know that the charge and the degrees of this algebraic Frobenius manifold will come from the eigenvalues and the order of the conjugacy class in the wild group. So if the order here is k plus 1, the charge here will be k minus 1 over k kappa plus 1. The eigenvalues also you can read. It will be correspondent with the degrees. So this is an example of D4A1. So we have dimension 4, and the universal deformation of simple singularity, it will be a map from 6 dimension to 4 dimension. And this is the reduction of the invariant polynomials in Slodov slice or Slodov coordinates. The 0 z's will give you a singularity of type D4. And the algebraic Frobenius manifold actually will be depends on this solution. So you have to get rid of the variable T6 and the variable T5, which here is quadratic. Okay, so for any quasi-coexistent conjugacy class or for any subregular Nilpotent element in DR, we can perform a Frobenius structure, algebraic Frobenius manifold structure, where the algebraic structure actually we know what is the degree. And we did the same things for another classes. For example, in the Lie algebra of type E8. This is a huge Lie algebra. We know the matrices are very huge and it have dimension 256, if I remember. And actually we could construct the algebraic Frobenius structure, and it will depend on, of course, 8 variables. And Z, here Z will be a solution of a quadratic equation. And the potential is very long. I cannot present it here because it has 300 monomials. I just write some kind of the first monomials of this one. So we have a huge numbers here. Okay, and it is 300 monomials, but these numbers cannot be simplified because we have also some monomials with coefficients equal to 1. So our problem until now still exists. We cannot do the algebraic Frobenius structure for all conjugacy classes in coexistent groups. This is the first thing. Second, this one also, this conjunction of these steps, we don't understand until now the place where we do this Dirac reduction geometrically. And also the non-degeneracy condition is not an easy condition to read. Okay, I will stop here. Thank you.